All right, so there are our PowerPoint slides. So it looks like it's working okay. And I turned the closed captioning on in PowerPoint in case that's useful to anybody. So it's always kind of interesting. PowerPoint does a pretty good job of getting my words correct, but I've heard it does interesting things with physics words. So we might get to see what that looks like. All right, so as you can see, we are going to start looking at free fall today with our comic there with Galileo. There's a story that Galileo supposedly learned a lot about free fall by dropping things off the Tower of Pisa. So he did contribute quite a bit to our understanding of the laws of motion, which we'll talk about as we get into Newton's laws. Okay, so what was our lecture about? Our pre-lecture. The main topic now we're talking about is we're going to start looking at one-dimensional motion with constant acceleration. So in other words, changing velocities. So if we look at first quantity we're going to look at is the average acceleration. Again, we're doing along the x-axis now, so in the x direction. And as you can see here, so what is the average acceleration? It's just the change in velocity. How much has the velocity changed in the x direction? Again, delta, remember, means change. Okay, so the change in velocity, the final velocity, minus the initial velocity. And keep in mind that in one dimension, we're representing the directions of our velocity with plus and minus signs. And then we divide by the change in time, the final time minus the initial time. So it looks a lot like our average velocity expression, except now we're looking at how velocity changes with time. So just like we did with position, we can also graph velocity versus time for a moving object. So here's an example of a velocity versus time graph for an object, velocity measured in meters per second. Those are our SI units, and time measured in seconds. As you can see in this case, here's an object that starts at time equals 0 with a velocity of 20 meters per second, and then each second passes by, the velocity goes down by 4 meters per second. So you can see that at 1 second it's down to 16, and at 2 seconds it's down to 12. So we've got a positive velocity getting smaller, and then at 5 seconds the velocity is 0, and then after 5 seconds the velocity starts going negative, as you can see there, and it ends up at 10 seconds at minus 20 meters per second. So remember, positive velocity means it's moving in the positive direction, so it's moving in the positive direction but slowing down, and then it starts moving in the negative direction and speeding up. So that's something to get used to, is looking at one of these graphs and trying to picture the motion, and we'll play around with that with the we'll go look at our moving man PHYS in a minute. But before we do that, I thought we'd again look at the slope. The slope, again, is always a useful quantity when you have a line like this. And we can see, much like we saw with our position versus time graph when we looked at the slope, that the slope means is one of our fundamental quantities, right? We look at the rise over the run, or the change in velocity divided by the change in time. And you can see that change in velocity over change in time, right? That's just our average acceleration. So the slope of a velocity versus time graph is the acceleration. And we pretty much will only be looking at constant accelerations. And since we're only looking at constant accelerations, the average acceleration will always be equal to the instantaneous acceleration at any point. The acceleration won't be changing with time. And now we can look at, for this particular graph and for this slope that I drew, the slope points I chose, we can actually calculate the average acceleration, and we can see that the final velocity was minus 8 meters per second. The initial velocity was 8 meters per second. Okay, so we get a change in velocity of minus 16 meters per second, and then we divide by the time elapsed, which is 7 seconds minus 3 seconds, which is 4 seconds. And so we end up with an average acceleration of minus 4 meters per second squared. So now we can see our acceleration units, meters per second squared. And we can see that the acceleration here is negative. And then that corresponds to our negative slope. So that's consistent. So when the slope is negative, that means your acceleration is negative. So the slope of your velocity versus time graph. It's important to not get your velocity versus time and your position versus time graphs mixed up. Okay, so that's like the first thing to do is figure out which type of graph it is. Okay, so we are going to have a look at our moving man PHET again. So I'm going to stop sharing this. Okay. All right, so let's have a look at our moving man PHET now. See if I can find him. Where did I put him? There he is, I think. There it is, perfect. Okay, so just like we did before, we're going to play around with looking at what the motion looks like. So just to start with, I am going to get rid of position and just so we can just look at velocity and acceleration. And one thing I did this time was I turned on show vector so that you can see which way these quantities point. So for example, if I made the velocity 4, then it draws a vector, an arrow. Technically, it's more of an arrow than a vector pointing in the positive direction. And say I make our acceleration 1 meter per second squared. Okay, and now we've got another arrow. Unfortunately, they drew it right on top of the first one. You know what? Let me make it 2. See if that helps. There you go. Now you can see the acceleration. Acceleration is the green one. The velocity is the red one. And then if we hit play, and we can watch what happens. Okay, so if we ignore the little part where he stopped moving and everything dropped off, okay, you can see that we had a constant acceleration, a nice straight line there, nice horizontal line, okay, which represents a constant acceleration, and we can see that positive slope on the velocity. All right, so now what I'm going to do is I'm going to give him a negative velocity, say, actually, no, let's keep him at 0. Let me think about this. Let's actually just give him a negative acceleration. So first I'm going to clear. Okay, so that was somebody speeding up. He was speeding up in a positive direction there. Okay, and now say he's sitting there at rest. Okay, and now he's starting at rest with a large negative acceleration, and we start him going. And now you can see, and we'll stop him there so you have a look, he's speeding up in the negative direction, okay? Both his velocity and his acceleration vectors are pointing in the same direction, and that's causing him to speed up, and so his velocity is getting more negative and more negative. And we have the horizontal line now below the x-axis here, well, technically the time axis, okay, which represents below the horizontal axis, which represents that constant negative acceleration. And we can see the negative slope over here, negative slope here for our velocity versus time graph. Okay, I'm going to clear that. I'm going to look at position again. I want to put him back to 0. So we can play around with things like, what if he has a positive velocity, but a negative acceleration? So maybe something like that. Okay, and I'm going to get rid of position again for a second. Okay, so say he's moving in the positive direction, but has a negative acceleration. And we start that going. And so you can see he's moving in the positive direction, but slowing down. And then at some point, he stops, turns around, and he comes back the way he came. And now he's going faster in the negative direction. And we'll stop him there. Okay. I don't know if you can see, I'm just going to blow up the acceleration scale a little bit so you can see it. Okay, and so this is an interesting result where we've got, this is similar to the position versus time graph, sorry, the velocity versus time graph I was showing you before, right? Where it started with a positive velocity, so he's moving in the positive direction, he slowed down, got to a point of velocity equals 0, right here, okay, and then started speeding up in the negative direction. So that's what it looks like for velocity and acceleration versus time. Okay, so now what we can do is have a look at the position versus time graph. So even though it was hidden, it was still being graphed. And you can see, interesting result, right? The position versus time graph here for constant acceleration is not a line, okay? It's a curve. And in fact, we're going to see that this is actually a parabola, okay? But the thing to notice on this curve is that it starts with a positive slope for the first 4 seconds, where the velocity is positive, but that's a positive slope that's getting smaller. Okay, and then the slope becomes 0 at the top. And then between 4 seconds and 8 seconds here, we have a negative slope that's getting steeper, and that corresponds to down here a velocity that's at 0, and then it becomes more negative. Meanwhile, we have this constant negative acceleration the whole time. Okay, so that's how, give you an idea of roughly how the graphs correspond to the motion. All right, so I'm going to stop sharing that one now. All right, and let's go back and see if I can get my PowerPoint to share. Okay, there we are, back to the PowerPoint. All right, so if we switch now to looking at, okay, my PowerPoint doesn't seem to want to be, oh, there it goes. It's just being slow. Okay, so we've got our 1D motion with constant acceleration here, velocity versus time. So here's again our basically our velocity that starts positive and then becomes negative. And like we saw before, that leads to a parabolic position versus time graph. Okay. Now in this case, just to point out, I decided to call position Y instead of X. And the reason I did that is because over here on the velocity versus time graph, this velocity was labeled up. So what you'll see is I tend to, if we're talking about vertical motion going up and down, then I tend to use Y. Whereas if we're talking about horizontal motion, I will tend to use X. And then when we get to combining the two together, I will always be doing that, where horizontal will always be X and vertical will always be Y. So, so just like I was saying in the moving man, if you look at this position versus time graph, you can see that at time equals 0, the slope is positive, and that corresponds to where the velocity is positive 20 meters per second. And then at time equals 5 seconds, the slope is 0, and that corresponds to where the velocity is 0 on the velocity versus time graph. So it crosses 0 here, and that's where the slope is 0 up here. And then if you look at another point, say over here, and that's at what, 8 seconds? Yeah, so at 8 seconds, you can see we have a negative slope, and we go over to 8 seconds here, and we can see that the velocity at 8 seconds is minus 12 meters per second, and so that corresponds to that negative slope we've got. All right, and so you can see how the two different graphs relate and how you can basically take one graph, for example, and relate it to another type of graph. And that's the first thing we're going to do, I believe, for a poll question. So this is our first poll question. So I'm going to attempt to make a poll with my other account. So we've got choice A. So have a look at that while I make the poll. All right, so there's our poll. All right, so the question is, which of those 4 velocity versus time graphs goes with the position versus time graph on the left? Okay, the blue one. And that position versus time graph, they're using S there instead of X or Y, and that's sort of just use S as like a generic position variable. Okay, so it could be, you could think of it as X or Y, it doesn't really matter. Okay, the question is, so remember, what do we know? We know that we know the slope of the velocity versus time graph is the acceleration, right? We know the slope of the position versus time graph is the velocity. Those are the things we know. We can't really figure out initial position from a velocity versus time graph. But those are some of the things we've learned so far. So see if you can use that to take a guess as to which of these. All right, I think we're going to do about 10 more seconds here. So if you're not sure, go ahead and guess. All right, let's do a 5-second countdown. So 5, 4, 3, 2, 1. All right, and let's have a look at the responses. Okay, so what do we see? We see that most people think that the answer is C. Okay, so let's actually have a look at what the answer is. So I'm going to stop that guy in that poll. Okay, and is it going to change for me? Yes, the answer is C. Well done. Why is it C? Well, it's because, as we were just talking about, the velocity versus time graph, or the velocity at any point in time, is always going to be the slope of the position versus time graph. Okay, so for example, so here, what do we have? We have, let's go and look at position first. We can see that for the first part of position versus time, we have a straight line, right? So that means constant velocity. The slope is not changing. And so that rules out the first two. It means it has to either be C or D, because C or D both have this constant velocity for the first part of the time. Okay, and then we see that the slope is positive, okay, for that first portion of time. So that basically means it's C, all right, because that's the one that has the positive velocity to begin with. Okay, and then what happens to the slope? We can see the slope then starts to decrease. It's still positive, but becomes smaller and smaller and smaller and becomes 0. And that's exactly what happens with C. The slope becomes smaller, and it's still positive, but it becomes smaller and smaller and smaller and hits 0. Good, well done. So that's one way to give you an example of how to relate your position versus time and velocity versus time graph. All right, so now I'm going to go on to acceleration again. One thing that's really important to get straight with acceleration is the signs. Okay, it'll be even more important when we start doing 2-dimension. So one thing to keep in mind, this was in the pre-lecture, when an object's moving when an object moving in a straight line speeds up, okay, its speed gets bigger and bigger, that means its velocity and acceleration must point in the same direction. So they have the same sign in one dimension. Okay, and we saw this with our moving man. And when an object moving in a straight line slows down, its velocity and acceleration must have opposite signs. They must point in opposite directions. And we also saw this when we had our guy start at 0 and we gave him a positive velocity and a negative acceleration. And we saw the first thing that happened was that he slowed down. Okay, so that's something it's really important to keep in mind, okay, because it can sometimes get confusing. And if you don't get the sign of your acceleration right in a problem, then your answer won't be correct. So for example, if I show you this picture of a woman on a motorcycle, this is from another textbook where they're setting up a problem. We're going to try and do some problems in a little while here. Does anyone want to tell me whether this person is speeding up or if they're slowing down? What do you think? Yeah, they're speeding up. Well done. Yes, because the acceleration and the velocity are in the same direction. So she's accelerating on her motorcycle. And then if we look at another one, and now we have a curling stone. Okay, stone, rock, I always get that wrong. What do we think for our curling stone? Do we think our curling stone is speeding up or slowing down? Slowing down. Well done. Yes, because we don't know what the initial velocity is here, but we know it's positive. All right, in the positive direction. You can see what direction it is because of the little x-axis drawn at the bottom, but the acceleration is in the negative direction. So good. So that is really important to keep signs. So I thought because of that, the signs are important, that we would do another poll. Okay, so go ahead and start reading these because there's a little bit of reading to do here while I set up this poll. Okay, I'm going to start the poll. All right, let's have a read now. So given the following one-dimensional scenarios, in which one is the acceleration negative? Okay, so we have a police car increasing its speed while traveling on a road due west. Assume east is the positive direction. We have a child is riding their bicycle along a straight path and is going faster and faster. Assume the child's velocity is in the positive direction. A diver slows down when they hit the water, moving downward at the end of their vertical dive. Assume the plus y positive direction is upwards, which is what we often do. And then the last one is both A and C. Okay, so we're looking for where is the acceleration negative? Okay, and what did we learn just now? We learned that if you're speeding up, that means your velocity and acceleration point in the same direction. And if you're slowing down, that means your velocity and acceleration point in opposite directions. And I'll tell you, this one's a little tricky. Okay, I think maybe we'll do about 10 more seconds. So if you're not sure, go ahead and guess. Okay, let's do our countdown. 5, 4, 3, 2, 1. All right, now let's show our responses. What do we got? Okay, so it looks like the largest group, A, not quite a majority, and then the next largest group thought it was both A and C. All right, so let's see what our answer is here. So I'm gonna get rid of the poll now. Here we go. All right. So the answer is A. So it is only A. Okay, so why is it only A? So if we go through and think about it for a second. Okay, so here's a police car increasing its speed while traveling west. Okay, but the positive direction is east. So that means if the positive direction is east, that means west is the negative direction. And if so, velocity is in the negative direction here, because that's the direction the police car is traveling. And its speed is increasing, so that means the acceleration is in the same direction as the velocity. Okay, so that's definitely a negative acceleration. Okay, most people didn't think B, which is good because that's a positive acceleration, right? The child is moving in the positive direction and going faster, so they're both positive. For C, what's going on here? Okay, so the C now, so plus Y is the positive direction. We got a diver moving downwards. Okay, so their velocity is in the negative direction, but they're slowing down. So if their velocity is in the negative direction, but they are slowing down, the acceleration must be in the opposite direction to the velocity, which is positive. Okay, so C is also a positive acceleration. Okay, so we're talking about where they're moving downward at the end of the dive and they're in the water here. Okay, all right, and slowing down. Okay, so that's why only A in this case for this particular scenario. All right, so let's now go on and look at our kinematic equations. So the other thing they did in the pre-lecture was that they introduced and derived these kinematic equations for one-dimensional motion for constant acceleration. Okay, where you've got your instantaneous velocity, your initial velocity v0x, and your final velocity vx, your acceleration ax, and time are the four variables that show up in our equations. Okay, and what you're going to do to solve problems is try to figure out which of these, and we're going to do this a couple times here, which of these is the appropriate equation to use for a given scenario, okay? And it's going to depend on what they give you in the problem statement. And then you'll have to go through and figure out which, like you can see all four variables nicely in this first equation, you know, which equation are you solving for? Which variable are you solving for? And basically you're going to need, you can see there's four things here. So you're going to need three of them to solve for the fourth. Okay, and then there are different combinations in each of these three, right, equations, and so that's going to help you decide, depending on what combination of variables you're given, which equation is the right one to use. Sometimes there's always more than one way to do a physics problem, and sometimes you can just, if you don't want to do the one problem example that involves the quadratic equation, you could use the other two equations to solve for instead. You could do a two-step solution. So there's often multiple ways to solve things. So I thought we would go back and look at our curling stone here that I showed you earlier, and sort of go through and see how we might solve this particular problem. In particular, we're going to try and solve for the initial velocity. You can see there's actually two unknowns here. There's the initial velocity is unknown and the time is unknown, which is interesting. Okay, And so, but we're, instead of solving for the time, we're going to try and solve for the initial velocity. Don't know time. And so which equation are we going to use here? Well, there's only one equation, our third kinematic equation, that doesn't have time in it. All right, so if you ever are not given time, it's likely that you're going to have to use this one. Okay, so this is the one we're going to use. Okay, so first what I'm going to do is plug in everything I know is 0, and then also plug in the equation, sorry, I keep saying equation when I mean variable, the variable names in the problem. So basically, I'm going to plug in 0 for Vx, okay, the final velocity. Okay, because we're told the final velocity is 0. I'm going to plug in V0 for V0x, because that's the initial velocity. I'm going to plug in A for AX, because that's the acceleration. Okay, just a variable for now. And then we have set, as you can see, and we're often going to do this, we're going to set the initial position equal to 0. Okay, so I plug in x0 equals 0, and that makes x minus x0 become just x, the final position. Okay, so one thing to notice when you do these problems, if you're not given a nice picture like this, and you're often not given a nice picture like this, the first thing you should do is draw a diagram like this. It doesn't have to be beautiful, it just has to be something that you can understand yourself, but I highly recommend, okay, in fact, in most cases, we're gonna require it as part of the structure of the problem, okay, that you draw your object, you draw in which way the acceleration is pointing, which way the velocities are pointing as best as you can tell. Sometimes you don't know. And that you draw in an axis. Okay, in this case, we've got our x-axis. And that you label everything you know about the problem. Okay, you label all your knowns here. We can see we've got our 3 knowns, 2 positions. Actually, we have quite a few knowns. We have our final position, we have our velocity, our final velocity, we have our acceleration. Okay, those are actually the 3 important ones we need here. And then you also want to label which things you don't know. So we didn't know initial velocity here, we don't know time. All right, so now we've got our equation. It's always useful, if you can, to manipulate the variables first and then plug in the numbers. So we've manipulated things. And now we're going to plug in the numbers. Okay, and don't worry about that minus sign. It's okay, because the acceleration is negative, and so it's going to deal with that minus sign inside the square root. Okay, and so now there's one more thing I had to do, which I didn't mention yet, which is that they gave us the acceleration, just to be difficult. Sometimes books do this. They gave you the acceleration in centimeters per second squared, but everything else is in meters. So, and you really want to try and do it in meters, since everything else is in meters. So I converted that 26 centimeters per second squared to 0.26 meters per second squared. I basically divided by 100, because there are 100 centimeters in a meter. Okay, and then I can't see my mouse. There it is. And then so then I plug in my acceleration. I plugged in my final position. Okay, we know it's plus or minus because we're doing a square root here. Okay, but then I decided, right, based on my original picture, that I know that it's the positive answer that's the answer I'm looking for, because we had made this assumption, the way we set things up, that the curling stone was moving in the positive direction to start with. So my answer is that the initial velocity was 3.8 meters per second. Okay, so all right. So, and what is negative? Someone's asking, well, what does negative acceleration mean here? It means that the object's slowing down, right? Okay, you can see it's slowing down. It starts with a positive velocity and it ends up with 0 velocity. And then you can also, sort of, if you know anything about curling, you can think about what typically happens with a curling stone. Often with these problems, it's useful to go back and then think about the real world and say, okay, what do I know about curling stones and how they move? And usually what happens is somebody starts it moving with initial velocity and it slows down. Okay, I mean, I know not all of these situations you'll know, but most of the situations will be things like cars moving or bicycles and things like that most people have a little bit of experience with, and so you can kind of relate it to your experiences in real life. Okay, so basically, in the absence of air resistance, all objects dropped near the surface of the Earth fall with a constant downwards acceleration. Okay, and I wanted to see if I can show you this. So people often find this hard to believe because, and I don't know why this guy is not going to play for me here. Why are you not going to play? I may have to stop sharing to make this play. See if I can get this to play. People had a hard time believing that things fall with a constant acceleration because, there we go. Let's try this. Because when you drop like a heavy object or a light object, it looks like they don't fall at the same rate. So, all right, does someone, okay, let me try and get that going. Do that. I just really quickly wanted to show you our free fall motion. So this is a video somebody took, and what they did, and I'm hoping you can see this. It doesn't want to play, and I don't know why. I may just have to post this for you. This guy doesn't want to play, so I'm gonna post this for you, and you can also see. I'm gonna grab this and put it in the chat so that you can go look at it if you want to see it yourself. But what they did was they dropped a bowling ball and a feather. And let's see if I can find this. Okay, I do actually have this here, so let me see if I can share it real quick. So I'm going to stop that one and see if I can share this other one. So, but they dropped a bowling ball and feathers in a vacuum. Okay, as you can see here, I'm going to try and get it to start going. And this is an enormous vacuum chamber. So rather than do it on a small scale, they did this enormous, and I'm going to turn the sound up. We don't really need the sound on that one. But the thing to notice is that they fall at exactly the same rate. If you take the air away, okay, boom, they hit at exactly the same time. Okay, which is just kind of amazing. It was hard to believe at first that that was the case. For people, but once they were able to like evacuate things like that, then they were able to see that in fact is what happens. Okay, so what is that constant acceleration? That constant downwards acceleration is minus 9, is the magnitude of it. So it points in the negative y direction, or it points towards the center of the Earth, vertically downwards, and its magnitude is 9.8 meters per second squared. So provided you define upwards to be positive y, which is what I always do, I always define upwards to be positive y, then you can say that the y acceleration will always be minus 9.8 meters per second squared. And then what you can do is plug minus g into your kinematic equations everywhere you see a, and that's what they end up looking like. Okay, so what I wanted to do was do an example problem for you, okay, of free fall motion. And I'm going to do a really quick poll question first for this one. So what do we have? We have a stone is thrown vertically upwards with a speed of 24 meters per second. And the question is, how fast is it moving when it is at a height of 13 meters? That's the first question. And the second question is, how much time is required to reach this height? Okay, so this is actually, I'm just going to get you to vote in the chat. Which do you think? Which kinematic equation should I use for part A, do you think? So I've got an initial velocity, okay, I want to know how fast it's moving, I don't know time, lots of votes for C. Yep, that's what I would have done too. That's what I did do. I chose C. See, this guy's going to work for me, C. Okay, so let's do it. All right, so like I said, first thing you want to do is draw a picture. So here's my picture. Okay, so here's my object. It has an initial y velocity of 24 meters per second, v0 y. y is upwards. They didn't tell you where it starts, so typically you choose starting position if you can as being 0. Then the final position is our 13 meters above that point. Okay, and we want to know how fast is it moving when it's 13 meters above that point. So we're looking for Vy. Okay, so again, we're going to use equation C here. Okay, and so let's start plugging things in now because we're going for Vy here. So we can just start plugging in. So we have our 24 meters per second. Okay, we have minus 2g. So notice, okay, the minus sign is already there. Whenever you plug in g, g is positive 9.8 meters per second squared. Okay, I will always do it that way. Every time I write g, it's a positive quantity. Okay, and then our displacement, our vertical displacement, y minus y0 is our 13 meters. And I think I really would encourage you guys to use y minus y0 or x minus x0. Don't use d, okay, because d, it's not clear what d is. Distance, displacement, we don't know what it is. I know sometimes you use that in high school, but I would prefer you not use d. Try to use your position variables here. Okay, so, and what do we end up with? Again, we end up with the plus or minus because this equation has that square in it. But again, that plus or minus is valid. It has physical meaning. Both answers are valid because it's the positive answer. The idea is that when you launch this rock and you throw your stone, you throw words, right? When it gets to 13 meters the first time, it's going up at 17.9 meters per second. And it's going to go up. Where's my mouse? There's my mouse. It's going to go up. And then it's going to come back down, okay? And when it comes back down and gets back to 13 meters again, it'll be going at minus 17.9 meters per second. So there's a symmetry here, okay, of the motion that when you're at that position of y equals 13 meters, whether it's when you're going up or when you're going down, in either case, the speed is the same, okay? Because you lose as much speed on the way up as you gain on the way back down from that point. So when you're starting at 13 meters, you've got 17.9 meters per second, you lose it, it becomes 0 at the top, and then when it comes back down, it's going 17.9 meters downwards. Okay, and so basically, both answers are valid for the first part, and then, but the speed for both of those is the same answer. It's 17.9 meters per second. So we have run out of time. So I did solve the second part of this. So what I will do is, I was going to ask you about the second part, but since we run out of time, we don't. But this is what the answer to the second part looks like. And you can see what you do is you solve for those two times. The time it reached 13 meters on the way up and the time it reached 13 meters on the way down. Okay? So that's where I am going to stop. And then if there are any extra questions, I am going to post the lecture slides, yes. Yes, you can, if you want to use the one with A in it, just make sure if you use the one with A in it that you put in the A is minus G. Okay, so let's see. So for the midterms, for the tests, I don't call them midterms, I would say that you should study everything, the lectures, the homework, the tutorials. And what does it cover? It's just going to be up through 1D and 2D motion, yeah. So CrowdMark will be released as soon as I post the first written assignment, which will be sometime soon. Okay, probably, hopefully today. There are not midterms, there are tests. It's all on the schedule. So yeah, chapters 1 through 3, I'm pretty sure. I'll let you know for more details once we get closer to the first test. All right, I am going to stop the recording.